Let's now talk about change of variables for triple integrals. So suppose that in xyz space, I have some solid region R. I want to integrate some function over this region. So I have a function f from R to the real line. But for whatever reason, this integral is unmanageable or inconvenient. So I'd like to use a different coordinate system, which we'll call u, v, and w. And I have some transformation t from the u, v, w coordinates to the x, y, z coordinates. So your x is some function g of u, v, w, y is some function h of u, v, w, and z is some function, I don't know, say k of u, v, w. And the region R corresponds to some other region, S. Okay, so t from S to R, we're going to assume is a differentiable bijection. So then if I do the triple integral over R of f with respect to volume, then that's going to be the triple integral over S of what? Well, first I have the composition of the functions as before, and then I have a magnification factor, and this is the absolute value of the Jacobian of x, y, z with respect to u, v, w. And then I have dv, where this Jacobian for functions of three variables, so that should not be z, that should be x. So d of x, y, z, d of u, v, w is the determinant of dx du, dx dv. Basically we just put all the partial derivatives into a matrix here. And then we have dy du, dy dv, dy dw, and dz du, dz dv, dz dw. Because remember, the determinant of a 3 by 3 matrix is the plus or minus the volume of the parallelepiped spanned by the rows. It's also plus or minus the volume of the parallelepiped spanned by the columns. And in this case, if you take a little rectangular box in the region S, then this gets mapped to something which is approximately a parallelepiped in R. And the edge vectors of that parallelepiped correspond to the columns of this matrix, multiplied by delta U, delta V, and delta W. And so when you take the absolute value of the Jacobian, then this is approximately, well, in the limit it's equal to, so it's the limit as delta U, delta V, and delta W go to 0 of the area of T of the box, sorry, not area, volume of T of the box divided by the volume of the box. Right, so this is completely analogous to the two-dimensional case. So let's do an example to see how this works. So let's look at changing to spherical coordinates. Okay, so we start with the usual xyz coordinates. Then we're going to switch to the spherical coordinates rho, theta, and phi. So here, this is what I was calling u before. So here u is rho, and theta is v, and phi is w. Okay? So I have my region R over here. It corresponds to some other region S over here. I'm not going to worry about getting the shapes of this region exactly right. But let's compute the magnification factor. So we know from before that the magnification factor is supposed to be rho squared sine phi. So let's calculate the absolute value of the Jacobian and make sure that it works. So first we have to remember the formulas for the transformation. So the transformation, t here, is given by x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z equals rho cosine phi. Right, so now we have to calculate this Jacobian. So Jacobian of x, y, z over rho theta phi. So the hardest part of this calculation is making sure that we don't get mixed up between theta and phi. Okay, so first we have dx d rho, dx d theta, dx d phi. Then we have dy d rho, dy d theta, dy d phi, and finally dz d rho, dz d theta, and dz d phi. So what are these partial derivatives? Well, so dx d rho, so I just look at the formula for x over here, and I get sine phi cosine theta. And dx d theta, well, the cosine theta becomes a minus sine theta. So I have minus rho sine phi sine theta. And then dx d phi, the sine phi turns into a cos phi, so this is rho cosine phi cosine theta. Okay, then the next row, so I have dy d rho, which is sine phi sine theta. Dy d theta is rho sine phi cosine theta. And dy d phi is rho cosine phi sine theta. Then the last row I have dz d rho, which is cosine phi. dz d theta is 0 because there's nothing depending on theta in there. And dz d phi is minus rho sine phi. Alright, so now I have to evaluate this determinant. So first I take the product of the diagonal here. So I have two rows. I have a minus sign. I have two rows. I have 3 sine phis, so I have sine cubed phi. And I have 2 cosine theta, so cosine squared theta. Next I take the product of this times this times this, which is minus rho squared. Then I have a sine phi and 2 cosine phi, so I have sine phi cosine squared phi. And then I have 2 sine thetas. And then I need to subtract the product along this diagonal. So I have minus rho squared times, I've got a sine phi and 2 cosine phis. And I've got 2 cosine thetas. And then finally I have to subtract, so this 0 times this, which is not going to come in. And then I have to subtract this times this times this. So I get a minus rho squared, and then I have 3 sine phis, and I have 2 sine thetas. Okay, so this isn't as bad as it looks, because if you look at these two terms here, then these are the same except the cosine squared theta turns into a sine squared theta. So I can use cosine squared plus sine squared theta equals 1 to write the sum of the red terms as minus rho squared sine cubed phi. And then if we look at these two terms here, we see that they're the same, except that the sine squared theta turns into a cosine squared theta over there. So the sum of the blue terms gives me minus rho squared sine phi cosine squared phi. Okay? And now, if we look at this again, we see that this is minus rho squared sine phi. We can factor that out, and then I've got a sine squared phi and a cosine squared phi, and those add up to 1. So this is it. It's minus rho squared sine phi. That's the Jacobian. Okay, so now you might be a little worried, because the magnification factor we're supposed to get is rho squared sine phi with no minus sign. And here we have a minus sign. But the magnification factor is the absolute value of the Jacobian. So it's the absolute value of minus rho squared sine phi. Now, minus rho squared is not negative. What about sine phi? Well, that depends on phi. Remember that phi, that's this funny longitude coordinate, always goes from 0 to pi. That tells us that sine phi is always greater than or equal to 0. So this sine phi is not negative, and so the absolute value of this is just rho squared sine phi, which is what we wanted to get. So that's good. It all works. All right. Now we're going to, in the next lecture segment, look at some examples where we're going to make up our own coordinate system.